Hello? Hello. Oh, okay, I think finally. Damn yeah. Sorry about that. Well, um, let's see. So I'm setting everything up so that I can take a look at everything that happens during the stream. There you go. So I can see the chat now. Oh, hi, Penguin Operator. Yo, perfect. Um, yeah. Welcome, welcome, welcome. If you're here. I'm going to get my water bottle. Get my water bottle. Okay. Let's stay hydrated. All right. So, how is everyone doing? Hopefully, everyone's well and healthy. Well and healthy. Um, today I am. I'm fine. I'm fine. I'm fine. Um, yeah. Once again, sorry for being a little late. Yeah. Just passed me by. I overslept a little, which is why you may see me like kind of dreamy. Um, ah, yeah, because yesterday I had to go to bed a little late compared to my usual bedtime. The reason for that is that I was cooking everything that I need for the week. So what I usually do is on a given day, I just cook a lot and then I just freeze everything. And every day I just go to the freezer and grab whatever I already have prepared. Yeah. Late, so 8 p.m. All right, buddy. No. No, no. No. I went to bed at like what? 11:30 my time? 11:30 p.m. So it was kind of late when I mean I usually go to bed at like 10. Right. It was either 11:30 or midnight. But I I prep all my meals. And the only thing I eat, and I kid you not, is burritos. Like burritos are the only thing I know how to do, not because I have some sort of Mexican heritage or anything like that, but because burritos, like one summer ago, I wasn't in an internship or anything, and I needed to manage my resources very well. And so I discovered that like burritos are very cheap when it comes to the ingredients, but they're also extremely nutritious since they have so much stuff. Like you can just put whatever you want in the burritos and then they're really nutritious. So I discovered that and that summer I basically just the only thing I ate breakfast, lunch and dinner was burritos every day for 3 months. So it's the only thing I know how to cook because of that. And I don't know, I just got so used to it that like it's this summer I'm just doing the same because the only thing I know how to cook. And like it's nutritious enough, it's very accessible. So I just dedicate one day to cook like 16 burritos and I just freeze them. 16, 20 around that ballpark, and I just freeze them. Then when I want to eat, I just go to the freezer, unwrap the burrito from the tinfoil little thing, and then just put it in the microwave, and then that's it. You know. Um, what is a traditional dish in Colombia? Oh, it's well, it really depends on the region you're in. Colombia varies a little from region to region. I'm not sure we have a national dish we have dishes that like are part of the regions, and as such, you could interpret us as that. I am from a region where the main dish, or like the traditional dish, is like a plate with beans, rice, eggs. This thing that's called the thing that I'm not sure what the name is in English, but it's like when it comes to a pig, when you grab the skin of the pig and also some of the fat that it has, that has a name. In Spanish is chicharrón, which is the funny name. Avocado, morcilla, which is also made out of like, you know, some of these are like very weird. Like morcilla is like a sausage that is stuffed not with the usual stuffing, but with like rice and some parts of like a pig's. I don't remember what it was. It's some part of the pig, so it's there. And corn. Yeah, so it's just like a plate that contains a bunch of stuff. And by plate, I mean like a silver plate. In fact, the name of the dish is bandeja paisa, which means like paisa plate. Paisa representing the people in the region I'm from. But yeah, gosh, is everyone's audio crispy these days? I just had two streamers back to back have all bad audio now. Also, hello, it just works okay. I hope the audio it's just working okay. So let me know. Is the audio bad? Like, do you mention that because you're like, oh my god, what's happening? Or did you mention because this audio is also bad? Let me know and then we can try and fix it. It just works okay. Okay, that's perfect. That's all I need to know. Great. All right. How is everyone else doing in this morning? Well, morning for me. For some of you, it's gonna be afternoon if you're in Europe. Yeah, let me know in the chat, and then yeah, you know, these days, these are interesting days. But yeah, all right. In the meantime, I'm going to transition. Also, I've been considering, the starting screen, this one. Been considering adding music to that. It's just that previously, if I added some sort of music, it would tank the kbps. It would like for absolutely no reason. Also, let me know if the stream ever lags. I'm seeing the kbps are like jumping around for absolutely no reason. Let me take a look at the stream from a different machine to see if what um what was that stream? Okay, let's see. Oh, there's almost no latency. Okay, that's good. And I see everything very well. So what happens if we transition to the coding scene? Like, is that okay? Yeah, seems like it, right? No lag. Gonna put the camera where it usually is. There you go. It's so funny to see that. I'm gonna put it over the little bar with the stats, because then you can maybe see, what column we're in and stuff. Yeah, I think that's perfect. Yo. Ooh. Ganga Kamau. Welcome to the stream. Yo. All right. If you notice me a little bit dreamy, a little bit, I woke up a little late, which is why we were late to the stream. Really sorry, guys. But yeah. All right. seems like everything's working. And I'm seeing the stream here on a different machine, and it is also working. Yeah, awesome. Okay, I'm gonna close this. I'm gonna place it in the place it belongs. This is my work laptop, and I'm using it just to check the stream for a few seconds, and not for anything else. Okay. All right. What should the title of the stream be today? So today we have coding a memory allocator from scratch and then testing free and red black tree. I feel that's also what we're doing today. like, so I think we can keep it like that. And well, maybe we can just put in the part two. Part two. There you go. Okay. So welcome everyone. Just to, just to have a little summary of what we did yesterday. We were looking at how to test our translation of the red black tree class that we had previously done in C++ and now needed to port back to C. So we were starting to do that, and we were running into some sort of seg fault, if I remember correctly, which honors very well the name of this channel. As such, we're going to see what happens when we try to execute the red black tree test, because I don't remember correctly if it was a seg fault or not. And yeah, hopefully it is not a seg fault, because seg faults are dangerous to say the least. So we create all the blocks, and that's completely fine. Oh, yes, yes, yes. Choo-doo-doo-doo. And then when we link, I think we have a problem here. Oh no, never mind. Here, no. Here, no. Here, no. Here, no. It's in the left rotate, right? Yes, there's a bad axis. So there's something that we're accessing that's just not it. I don't know what it could be. Because in the red black tree test, we're having like 1 megabyte of heap. So that should be totally fine. Yeah, I'm not sure. I'm not sure what's happening. What's happening? Okay, let's take a look at it. So all of this is fine for us, right? So we continue here. And in fact, I'm gonna just place a breakpoint over here. Then we're gonna get into this function. So let's see what happens. This assertion should go fine. We set the parent of our block is the 0th block. And that is indeed the case because we're rotating at 5, which is the first block we ever created. So that's fine. We set its parent. Then we say, well, the parent of my block is different from p pointer. Then we're gonna do stuff. So, let me first delete all of these values that we have here and keep only the relevant ones. So I want to see who the parent of my block is. The parent is null, so we just don't do anything. Oh. Hello. What is going on? Oh, wait. Oh, okay. Why is the parent... Okay, I think that's the reason why we're failing everything, because we're somehow accessing a parent that just doesn't... I see. So when we create block, we not only want to set the size, but we want to set everything to the default. So set left, right, and the new block to be like a null heap pointer, and we just do the same thing for both the right and parent. Because if not, then the thing is going to think that we actually have a child or a parent, and it's gonna try and update those. But if they have just completely bogus values, then that's that's bad. So set the color. Maybe we can just set it to red or something like that. I don't know. And set the is free flag. Let's set it to true. True. Okay. I think that fixes it. And we'll be able to take a look at it. Then if we run it again, we should be able to see that everything is working. Okay. So today we have main, right? We continue here. Then we take a look at the left rotate function, and now it should be able to see that there really is no parent. And it should skip this sec. Hello? Well, what is the... I don't think we can access macros. Yeah. So what is the value of a null hit pointer exactly? It's 295, and this is a 294. What? What is going on? 429, 496, 729, and then a 4. What? Okay, wait, let's see. What is happening? So if instead I access the BK parent of 5, oh, error? Oh, wait, because we haven't reached that function. Yeah. It says 429, 496, 7294. But we set the parent to be the null heap pointer. Is it because we said that is free? Are we doing something wrong right now? We set the parent, and for that we... Wait, no, this seems to be completely fine, right? BK parent, BK header, and then we... Yeah. No? So let's see. Let's see, this is very strange. Why is the parent a heap pointer -1? That doesn't make much sense. So here is where we're creating 5. And now I want to take a look at what the parent of the new block is. And it's currently 0. But after we set it to null heap pointer, it's this 294. Oh, guys, we've been having a serious problem. Ooh, okay, this is an interesting bug. So the bug currently is the fact that when we go, so remember, I'm gonna go to the Allocator for this. Remember that when we're talking about the parent, since the parent has its least significant bit being used for the sake of storing the color, right, here, what we end up doing is, suppose that the parent is like 1 byte long, right? So it would be 1, 2, 3, 4, 5, 6, 7, 8, right? 1, 2, 3, 4, 5, 6, 7, 8, right? Suppose that when right, suppose that this is a Coding Barra said this is good audio. Yo, let's go. And Coding Barra, welcome once again to the stream. Yay. We're explaining a bug that we just found. So the bug is this, right? Imagine parent is 1 byte. We know that we're borrowing the least significant bit to set the color, right? To say, like, 1 or 0, 1 for black, 0 for red, and so on, right? The thing is, when we return from the BK parent function to obtain the parent, we only obtain these bytes over here, right? We only take these bits over here, right? We only take a look at these, right? And so what ends up happening is when we return, we always know that this last bit is 0. And that is true for every single sort of, you know, block that actually lives in the heap. The problem is when we compare a parent to a null heap pointer, the null heap pointer, it's going to be the maximum value that a uint32 can take, which is all ones, right? So 1 and then a 1, and then in here a 1 and a 1. I don't know why Allocator doesn't have. Let me see if I can change the font to be like code. Yeah, 1 1 1 1 1 1 1 1, right? So this is what the maximum uint32 is, which would be our value for a null heap pointer. The thing is if we set the parent to have null heap pointer, just to indicate that there is no parent, we're going to be setting all of these values or bits except for this one, because this one is reserved for the color. So if you set the parent to null heap pointer, what you end up with is this. So you end up like 1 off. So when I compare these two, I say set the parent of this block to be null, and then we ask, is the parent equal to null? It's going to say no, right? Because this last bit is different from the bit it should be, just because of the way parent behaves. Yeah, that is interesting to say the least. So, So how do we solve this, right? There are multiple ways to solve this. One of them, hear me out. One of them could be, I don't know. Could be, I don't know, because we have a serious issue. Very serious issue. So why am I saying it's a relatively serious issue? Like, I think I have a solution, but either way. So for size, you could be saying like, oh, why don't we just store it, the color, we maybe put it in right or put it in left. Well, we would have the same problem. If we have to signal that this node has no left or no right, we would need these values to be a null heap pointer, but then the color being there would stop that from happening. If you say, well, how about we store it in size, right? Maybe if we store it in size, everything is going to be okay. And the problem is, well, we cannot really do that, right? The reason being, we're currently using size, its last 2 least significant bits, right? We're using 1 to indicate whether or not the previous block is free, and we're using the other one to indicate whether or not we are free. And so that's, from size, we can at most spare 2 bits because it's 4-byte aligned, right? You would think it's 8-byte aligned, but no, size it's special and it is 4-byte aligned. So I think the solution will be to transfer color to size and simply just not use the current free bit, because I don't think we're using it anywhere, right? Like, if we are already storing the previous free, why are we storing the current free? it seems to not make much sense, at least not to me, right? Because we're already storing, it's like we're duplicating the amount of storage that we're using for like absolutely no reason. There might be a reason that I'm forgetting, but it seems to be like there isn't, right? So if we go, for example, here, when we go to the isFree function, there you go. So what happens here is we end up using the least significant bit for free, the second least significant bit for previous free, and then we end up using the rest for size. Why are we storing free? Right? It's like, yes, and maybe it's easier, but if you just go to the next block and grab its previous free, you'd be able to know this information. And then we can repurpose this free to represent the color. And that gets rid of all of our issues. So let's see if we can do that. Currently, we are obtaining the whether or not this block is free by taking a look at the least significant bit. So instead of that, we're just going to take a look at, the BK, the previous free of the next block. And I think that solves everything. Too few arguments to, I'm sure this is just the extension. Yeah, the extension being slow. So to know whether or not a block is free, we just look at the next block's previous free. To set a block to be free, we don't really need to do this anymore, right? We need to simply set the previous free of the next block. Okay? Yeah. And I think this just fixes everything. And now to set the color, right? So now we need to change the color function. Now color is not stored in the last bit of parent. It is instead stored in the last bit of the size, previous free, and free field, which in fact should be renamed to size, previous free, and then color. So there you go. All right. So what we do is we obtain the least significant bit of the size guy, and this seems to be fine. Okay. To set the color, we do this exact same thing, but for the size previous free color field, right? And then we should be fine. And for the parent, we just act normal, right? For the parent now, this doesn't need to have an obscure value. It can just be called parent. And here, instead of doing all of this, we simply return whatever the header says the parent is. And to set the parent, we simply set it. There's no need to perform any sort of bit manipulation. Perfect. I think that's exactly what we want. Oh, yeah. These guys just changed their name to SPFC, right? Awesome. Okay. Oh, wait, no, not SPFC. It's underscore SPFC. And that should work if the extension is fast enough. Yay. Perfect. So I think that changes our design to store color in the least significant bit of size, just so that we can have the whole parent thing whenever we have a null pointer. Perfect. Okay, I think we're good. I think we're good to go. Right? Yes. Awesome. Okay. I think there is no more complaints anywhere else. And there shouldn't be, because these functions are supposed to be the only source of truth. So if we ever find a bug where actually they were not the source of truth, that's going to be great because they're supposed to be. So let's take a look. Let's see. Yeah. So we enter the heap size, great. Now when we set the parent, we should be able to see the actual value, which is the one that ends in a 5. Yes, 429,496,729,5, which is the actual value we want. Now we can continue our lives being free. So we get to the rotate function. And when we enter here, we know that this node has no parent. And we should skip this section, which is indeed what happens. Perfect. So let it run from now. Oh, well, what is the problem now? So let's take a look at the code stack. Do we have any sort of output on what the failure was? I mean, I know it's this assert, right? But okay, I do want to print and see what it is. Oh wait, no, I could have just taken a look at the debugger. Sorry about that. Okay, we left rotate, and now we can take a look at what the arbitrary to vec function produced by simply going to the vec tree thing. So it produces 100, then 48, 20, 80, 60, 88, 120. What are these values? Why are they 48? I think it's doing the right thing. So first of all, this stopped being a 10 and every single one of them was multiplied by 10. So we should be seeing this, 150, 20, then 80, 60, 90, 120. But there is the problem that some of them are just not returning the right thing. So did I mess up the size function when we were taking a look at this? I shouldn't have, right? Oh, I think I know what it is. Okay, so we have the assumption that size is always 4 byte aligned. And as such, these values are not 4 byte aligned. So I think we can just do the following. Maybe we just multiply things by 4, right? 5 times 4. Yeah, I mean, 2 times... Let's just do it with multiples of 4 from the start. So maybe we can do 16. Well, no, I want it to be 5. Okay, I'm just gonna include a times 4 here. So maybe 50 times 4, 100 times 4, 80 times 4, 120 times 4, 60 times 4, 90 times 4. Just so that they're aligned. 100 times 4, 50 times 4, 20 times 4, 80 times 4, 60 times 4, 90 times 4, and 120 times 4. Okay, and that should be fine. So that should be the last thing we look at. Yeah, so if we run it, it should succeed. So then, Pingu! All right, you guys starting to know each other. That's great. Oh, perfect. It passed. Right? No failure, no anything. So it seems like the left rotation test we had is working, which is more than great. Okay, perfect. So now that we know how everything works, we can just keep quoting all of these tests we have over here. So what we're going to do is, okay, so it seems like here we created a function called arbitrary equals vector, which is actually pretty convenient. So let's do that. We have a bool arbitrary equals vector. And what we're going to accept is a red-black tree. So it would be like a heap pointer to some sort of, root or something like that. Some sort of root. And actually, no, we need to accept the actual red-black tree type, right? Yeah, because I think that from now on, we're going to test insertion and all of that. Yeah, so arbitrary equals vector. And then we're going to accept whatever the vector is that they want us to compare it to. And I think, oh, you cannot really access the size of a vector in C. You can in C++ through templates, but it's fine. And so what we're going to do now is we're going to just perform the usual comparison, right? So we create a vector called actual, and actual is going to have the same size as size. And, oh, is this going to be like you cannot determine the size of the array at runtime? I think we're fine. Int actual size, then over here, we're just going to do the arbitrary to vector. We convert this arbitrary to a vector, right? And I think that what we can do is we just grab the root of the red-black tree instead. Yes, perfect. And actually, this is totally wrong. We first create the array, and then we pass it to this function so that it can populate it. And then once we've done that, we are actually just going to, do the same thing we did before. So as we loop through the array, we simply assert that each value is indeed equal to the thing that it should be. So expected should be the name. Instead of actual, we should have vectory. Vectory, perfect. And then we return true if everything goes well. And instead of this, we would say, well, if, right? If this doesn't happen, then return false, and then otherwise return true. Awesome. So now we have this function to compare a red-black tree to a vector, and it's going to be really simple and easy because now that we're going to actually, so an example would be the test insertion case. Over here, we're creating like a red-black tree, right? And so we create a red-black tree ourselves, arbitrary. And what we're going to do is we can sort of initialize it in the same way we do inside the memory file. I think, yeah, over here, where we perform all the padding and all the ghost node size and all of that. This thing is what needs to be inside a red-black tree test. Maybe here, so arbitrary t, arbitrary, and then we say something like create a red-black tree, and then point me to the place you want me to. Actually, we can just put this, right? Yeah. And so what we do is we create a red-black tree here, arbitrary. And then by the end of the function, we return it. Perfect. And so once this happens, I think we don't need to fix anything. Once this happens, we can simply say, well, let this red-black tree be equal to, well, create me a new one, right? Create a red-black tree. And then we can start playing with it. So we can do arbitrary insert and insert into the red black tree maybe a new block, right? It is a little tedious because, well, I guess we just do create block, right? And then the size of the block. But not only that, we want to specify some more stuff. Okay, I think that what I'm gonna do once again is going to be inside the red black tree file, right? This red black tree to vec needs to be a little more structured. So I think if we just create a struct that's called node, and inside of it we store the same amount of information that we have for this guy, which should be, well, the color. We also save a pointer to, well, not a pointer, right? A heap pointer to the left child being equal to a null heap pointer. We also save a right pointer to the left child null heap pointer. And then, oh, I think C doesn't have default values, so that's unfortunate, but I think we're fine. And then we pass in a parent, and finally the size. And so that way we can allow the people that are debugging, oh, what happened? UN32T is not a type. So did I not, wait, I'm importing a standard int. Is that not the place where it's there? I think it's just the extension acting up. This always happens. Hello? What? All of a sudden it stopped working. Oh, is it because I haven't included the semicolon? Oh. Okay, well, perfect. So now what we have here is this node structure. So when we actually implement the function, we ideally return not an array of result, but an array of node. And so that way, hello? Oh, okay. Just type def this guy struct to be called node. Perfect. So we have an array of node that we can use so that we can inspect thoroughly the red light tree, right? Yeah, and so what we do now is we say, well, result size, it's gonna be this. Oh, what happened? Oh, sorry, I shouldn't be dereferencing, it's a pointer. Hello, indirection requires a pointer operand. Yeah, what do you think I'm doing? This is result. Hello? C++ extension, are you there? I think once again, this is the evils of the extension. So we're going to simply access the fields. So color will just be to bk color of that block. The left is going to be exactly the same, bk left of the block. Then we do bk right of the block. And finally we do, which one? Parent. Parent, and then take the bk parent of the block. That should be more than enough. And this should be an underscore. Aye. Perfect. I think we're good. Good to go. Use of undeclared function bk parent. Oh, yeah, the extension is just being slow once again. Perfect. And everything should be working fine, right? Return 1 times size of node plus L elements. Yeah, okay. Well, actually, I think it's better if I simply just do this size of node, and then here I do size of node plus, actually this times 1 plus L elements. That should be fine. Extension, please confirm. Okay, so now we have access to a lot more stuff in the red black tree. And what we can do is we can create an array of node instead, pass it to the actual function, and here when we're comparing, just take the size field and compare it with expected. The thing is, expected should also be an array of node. And so I think, guys, I have one question. In C, does comparing, like, is comparing structs a thing? Can you just compare a struct to another struct and the language would just go through every field and run the operation? I think it's an important question because I don't think it does by default, something like that. Yeah, so here we don't really care about the color. So we're just gonna access size. You can mem count, but not really. You compare either their memory address or a value. Yeah. Okay, that makes sense. So I think we can just access size here. Oh, sorry, this would be dot size. And this here would be dot size. Perfect. And so now this function works. And so should a sort of easier approach, I imagine, I suppose. So vectree should instead be a node array. And expected should be a node array. We also have there's no such thing as like a C constructor, right? So we have to instead create like okay. All of this just to make debugging a little simpler. Extern, it returns a node, and then create node. And that's, you can pass me the size of that node, or you can pass me the color and then the size, or you can pass me all of them. Node, create node. I'm gonna call it node for now because it's gonna be a function that we're gonna use a lot. So node, unless there's already a C function that's declared as node. It seems like there is. Function declaration for node, not found. Oh wait, C doesn't have function overloading, right? Oh, that's gonna be a problem. No. Yeah, I don't think it does. And it's one of the things that okay. Makes me appreciate the beauty of C++. Color, doing 32T size. Then we can pass the left, then the right. And then the parent, I suppose. That's what comes next. Perfect. Right. There is no function overloading in C. Wait, what does that mean? What does that mean? Oh, what you see is what you get? Yeah. Yeah. Anyways, it's fine. So maybe we can do how do we solve this? So because I don't wanna keep passing in all of the values when I just want to set when I just care about color and size. So I'm just gonna preface them with like size, right? Then color and size node, and then the normal node. Yeah, okay. It's gonna be a very funky solution, but we don't need it to be in the actual code base. We just need it for the tests. And then when implementing these, we can just say, okay, node, S node. It's a node that we're going to initialize just by accepting the size, right? So we can return return a node struct built from, I think the CS accept something like this, where I can just initialize all of the fields from here. The fields are color, left, right, parent, size. So color, you don't care about it, so red, color, left, right, parent, size. I think I need to include node at the beginning. It tells me type name not allowed. What do we mean? How am I supposed to return a struct? Is this the way that it should be working? Because I think returning this should be fine. No. Seems like no. Okay. So do I just create a variable and naughty and then just make it equal to that? And returns naughty. Expected semicolon after return statement. Brother. Semicolon is right there. Ah, these I'm going to I'm going to crash out. Okay, perfect. S node. Create node, and now we create the CS node, which specifies both color and size. So now our naughty is gonna have the exact same things. It's just gonna be a little different in the sense that the color changes to be whatever color specifies. For the last constructor, this is just node, we accept all of them, and in fact, I'm just gonna copy the signature from here. Perfect. And then we're just gonna make, oh wait, naughty is not returning anything. So we return naughty, then we make node naughty, it's gonna be equal to, and then everything just has the value that it's being passed. So left, right, parent, left, right, parent, and size. Yeah, that's all of them. And then we return naughty. Yay. Oh, Fambjerg, welcome to the stream. Man, I love Wayland. I've been on Winslov so long that opening up a window fast feels like alien technology. Let's go. Let's go. You good? Okay. I think we're good to go. And I think that with this, we are now able to compare only the size, not only the size. So this should be a dot. This also should be a dot. Perfect. Perfect, perfect. So, yeah, actually, I think that no, this guy can just be an int. And then we just compare the expected size with whatever it is. Perfect. Okay, so the left rotation, I spent like a week cleaning up after my failed attempt of using agents to make my Wayland implementation, brother. No, don't give in. Don't give in. Yeah. The agents had all the right functions and functionality, just put together horribly. No. Unfortunate, unfortunate. The Yeah, it's sometimes very difficult to get them to like write something like a cohesive thing if it's really big. It had flickering crashes. No, I imagine. It's the constant complaints with AI. You can stay in JavaScript. Brother, no. I see, I see. Ah, okay. Let's see. Let's see. So you can create a block of size 15. And then here we assert that the red black tree is equal to the following vector. And my red black tree. And then I just pass in the array. And which should be well, yeah, we cannot do this. Okay, that's unfortunate. Maybe we can do this CS node and then black 15. Can I just pass an array like this? Like a temporary array that doesn't really exist? I don't think so. Ah, ah, okay. I'm gonna crash out if I keep using C. C was so nice up until this point. Oh, sorry, the brackets go here. So it's only one, right? Can I just not pass an array like that? Is that just completely prohibited? I think so, right? Yeah. Okay. Well, I think we can just, I mean, we can circumvent this quite easily by just creating an unexpected array and making it just huge, right? So let's make it like 32 nodes long. This instead of a pointer would become a normal guy. And now what we can do is, can I do this? Can I do that? Can I be like, CS node and then black 15? Is that allowed? No. No. I still have missing features, but it's now falling. Oh, it's not falling apart, and I can actually maintain it now. Great. At first, my fear was, how am I ever gonna maintain this? Yeah, that's true. I mean, maintaining is, if anything, the hardest part, I imagine. Especially if you're coding a UI. Wayland, I think they recently changed like a bunch of the names of their settings. Now they're adapting to Lua like this. No, sorry, that was Hyperland that was doing that. Anyways, yeah. Interesting. I cannot believe I'm looking this. How to initialize a C array. Initialize an array in C, methods and example. It is really embarrassing. I know, I know, I know, I know. Please don't kill me. Uh, but it. Can I just not declare it and then. What the hell is this? Huh? Does anybody see what I'm seeing? What is this? Huh? I have never seen this syntax. So C implements the most obscure type of syntax, but is not willing to implement defaults for structured initialization. Ah, okay. Um, hmm. Oh, valid only for GCC. Okay, okay. So it's not C's fault. It's GCC's fault. Um, can I just not like I declare it and then I initialize it to this value? Can I not just do that? It seems like I can't, but I should be able to, no? So if I do node and then I create one, yeah, now it works. But if I do this, now it doesn't. Do I need to do it like this? Hmm. That is deeply unfortunate. It's okay. We're just gonna, occupy a bunch of memory and not really care about uh, the fact that we're gonna have like 10 things in our stack. I think we can just rename this to expected one and then expected one, exp1. So can you pass an initializer? Okay. How to pass an initializer list to a function in C. Is that a thing we can do? How to pass an initializer list as a function in C? Yeah, there you go. This guy has the exact same question as us. Yeah, something like this. Something like this would be awesome and great. Let's see. Write a wrapper then. Huh? Wait, this is using C++, not C. Right? Oh, it's C++. Okay, of course. Oh, of course it's C++. I guess we can use the AI overview to see if this answers our question. Ooh. Ooh, okay. This is the way in which you can pass anonymous arrays. I was looking exactly for that. Perfect. Best Creeper 21. Welcome to the stream. It's your first time in chat, it seems. But yeah, welcome, welcome. Of course, it's always C++ when you need C answers. Yeah, unfortunate, but I guess like we got the answer we were waiting for, which is we didn't want to create a bunch of arrays in the stack. Well, we're still doing that, but like I just want to hide that fact from everything, because now we can just convert this and say CS node black and then 15. Yo, let's go. Okay, now it looks exactly what I wanted it to look like. Perfect. So now we can assert and say, okay, and when I need C++ answers, I end up with Rust answers. Really? Yeah. Okay, now it looks like what we wanted it to look like. So basically, all of this sort of syntactic sugar that we were creating is so that we can easily test the red black tree. Because notice that now it's gonna look very sort of understandable, right? Something like what we did in C++, where we did the, this is my red black tree, does it look like this? And then we just simply specify the pre-order traversal of the red black tree to have it simpler. I think we can just do the same thing now. So if we do something like, insert into the red black tree, and then we insert a new block, say create the block of size. Remember, everything multiplied by 10, so 150 and 150. Oh, actually, we need to multiply things by 4 now, because everything needs to be 4 by the line. We're gonna create a block, that is of size is what? So 15? Size 1? Well, okay. Yeah, this is not very nice. What's that? 150. I can create one of size 10 times 4. And then the tree is gonna look something like, does my red black tree equal this vector representation of a red black tree? Right, 2. And then CS node. So now the root should still be 15. 15. And indeed, we were not inserting 1, we were inserting 5. So 50. Black. The root is still 15. And the next node, it's gonna be a red 5. Perfect. Okay, so things are just gonna look like that. I think the trickiest part for me with Wayland is the fact the core protocol is so lackluster. So I needed to use some extensions that not all compositors support. Wait, what is the definition of lackluster? I've heard the word, but lackluster meaning, is it like disorganized? Like difficult to pass through? Something that is uninspired, dull, or lacking in energy, effort, or brilliance. So I imagine, yeah, it would be difficult to parse or very, very badly written, maybe. I see. So you sacrifice the compatibility with ease of development. Because we create a block and multiply by 4. And finally, we assert that our red black tree looks exactly like the thing. I'm going to give it node. And then we have 3 of them. And it's going to be CS node. So now the root is the 5. So black 5, then a red 1, and then a black 15. Right? No, a red 15, sorry, because if not, we violate the rules of the red black tree. Finally, we pass in the size, which should be 3 nodes. Perfect. Okay. Now we're gonna continue translating whatever we see on the. I guess I feel like I can just grab this and find a way to edit the text sort of more easily. Maybe we just do this. So when we do arbitrary insert, find all the instances and replace that with arbitrary insert, and then pass in the arbitrary, and then a create block. Oh, sorry. A create block that spans the entire number that you just gave me, multiplies it by 4, and closes the parentheses. Yes, okay, every line is fine now. And then we assert this. When we assert the red black tree equals to that, what we're going to be doing instead is not passing a reference to it, but the actual, sorry, not passing a pointer to it, but the actual red black tree. And when it comes to the array, we're gonna need to enclose this into a node and then some sort of number. I'm just gonna put 1. We're gonna have to change this individually for each. And now, when we do this, right? So, okay, yeah, I guess this is a singular edit because now we need to do CS node and then passing the two values. So CS node, sorry, CS node. Okay, we're gonna grab this and find all instances of it. This guy, all instances, all instances. Yeah. Then we're gonna do CS node of whatever that is. We jump in a word, jump in the next one, and jump in the number. Delete the two parentheses and now include an actual parenthesis there. And things should be fine now. Yeah, the only thing we need is now the size, which we can do rather easily because here we have, let's see, here this should be 4, and thus this should be 4. Perfect. Here this should be 5, and thus this should be 5. Here this should be 6, and this should be a 6. Ooh, Maya Stellar, yo, welcome to the stream. Hello. For red black tree, why is it being explained in like parent or uncle way, like family property? Most of the explanations are this way, and I get confused. Do you know any better mathematical explanations? So you mean like what it means to have a parent or uncle and why we're using it that way? Or like what do you mean? What do you mean exactly? Like why they're using the parent and uncle and all of these family properties? So yeah, what is the question? Like, do you mean the concept of an uncle is confusing and the concept of a parent is confusing and the concept of a sibling is confusing? Or what do you mean? While we wait for your answer, we're going to keep adding these little numbers over here. So this one should be a 7, if I remember correctly. And then here we're gonna have a 7. Oh, I saw the message. Give me a second. We need an 8. Perfect. Yo, let's go. Okay, we ported the entire test to C, and it should be able to work. So this is a little bit of a, the queen test, because this thing is gonna perform multiple rotations as we go. It's gonna color everything the way it should, and so on. So let's call that test over here. Test insertion. And so at the end, I think it's good if we just simply print something like, the same thing we had there, which is success, and then a little guy with glasses. Yo, success. Perfect, and then a new line. Awesome. So let's see if we execute this, and then we run the red black tree test. I think there's going to be some sort of segfault issue, and I am now seeing it because all of these values, I completely forgot, they need to be multiplied by 4. Remember that. And they also need to be multiplied by 10. Yeah, okay. Let me grab all of them. Perfect. So we go to the right, to the right, to the right again. We add a 0 and we multiply by 4. Perfect, because all of them have to be 4 byte aligned, right? So this with 15, because I think 15 is the root, it's 150 times 4. Perfect, yay. Okay, now we recompile this. We recompile this. And then we run it. Okay, let me see. /arbitrary test. Assertion failed. Okay, we'll take a look at it before, but let's read the chat first. So, Maya Stellar, so your question, you say when like they use rotate the tree, balancing the red black tree. Yeah. So you mean like so is it like why when we rotate a tree do we have those specific cases? Because when we're rotating a tree, or like, well, not rotating, but balancing the tree, when we're balancing the tree, we have like a bunch of weird cases where it's like, yeah, it's like case 4. If your sibling's color is red, then do this. If your sibling's color is black and both of its children are black, then do this. Like, do you mean like why are the cases that way? Like, why is it that my sibling's color, returns, makes rotate a certain way? Do you mean like how does a rotation work? Let me know which one of the two. Is it like I know how rotations work and I know like how to rotate a tree? I just don't understand, like just don't see the reason why the cases are the way they are? Or is it like, oh, I'm not sure what it means to rotate a tree? Ooh, let's see. We have more messages. Penguin Operator says hi to Maya Stellar. Yo, let's go. Maya Stellar says hi back. Carl's Deb, hello. Why are you making a memory allocator? Hello, Carl's. Well, just for the sake of learning, I would say. is the main reason and the only reason. I didn't know anything about memory allocators before this, so I wanted to learn about them. And I feel like one of the best ways of doing that is by doing, right? Learn by doing. Yeah, I also wanted to stream programming to just meet other people and have other people join the stream and so that we could learn together and, become better at coding and understanding all of these concepts. Yeah, it's just for the sake of learning because there's thousands of implementations of better allocations out there. And I don't think I'd be able to write an allocator that could compete with, say, JMalloc or malloc itself. But yeah, we just do it for the sake of learning. So hopefully, you guys enjoy it and feel free to ask any questions about the design, about something you don't understand, because that's exactly the purpose of this. I am a beginner when it comes to memory allocators, so no one should feel bad by asking anything. At least it's not a sec fault. Oh yeah, I imagine you refer to this thing over here. Yeah, to the sec fault that we just got. Ah, no. Yeah, it's really bad. But it's okay. It's okay. And I see that Maya Stiller, you have a message. I pulled this explanation for the insertion of new node. If the parent of this new node is red and color of the parent sibling is red, recolor the parent. The sibling and grandparent nodes to black. The grandparent is recolored only if it is not the root node. If it is the root node, recolor only the parent and the sibling. This whole relation messes my mind up. Reminds me, do I have an allocator in a project to make slightly better? But yeah. The Lumen, welcome to the chat. Madman. Yo, thanks you. Let's go. POV being a bitmap allocator. But yeah. So Maya, you said this whole relation messes my mind up. And yeah, kinda. Like the relation between the nodes, I feel makes a lot of sense, right? Because it's almost like if we were looking at a family tree. So I'm not sure if that is the one where you're confused. I don't think so. But like when it comes to parent and sibling, those are sort of very natural, I would say. So if we have this little guy called Z, Z's parent would be this because, of course, it's the parent is the one right above him. Z's grandparent would be this guy. because it's the parent, right, of his parent. So Z's parent is this, and then the parent of this guy is this. So this is this Z's grandparent. And then finally, the sibling would be maybe a guy that would be living here, right? My parents' other child, which would be this guy. An uncle would be the same thing, right? My parent, who is my parent's sibling. So then we go up and find the grandparent's other child. So I think if you're confused on that, I just mentioned it. I don't think you were confused on that. I think the whole thing is like why the cases are that way. Like, you know, if my sibling is red and my parent is black, then we are going to rotate the tree and do all of these sorts of stuff, kinds of stuff. So the reason I feel is, at least in when it comes to insertion table, I think there is a table with all of the cases. Ooh, it's lagging a little. Sorry about that. Do we have a table of all the cases? No, I don't think so. Okay, so the reason why the cases for the red black tree, at least my intuition for it, and like I haven't thought deeply about it, but everything has sort of a reason, right? K0, when the new node is a root, we need to make it black. Well, this one's pretty simple because to obey the properties of a red black tree, you need to have a black root. You need to have every path to a black child, sorry, to a leaf has the same amount of black children or black nodes along the way. You also need the fact that the child of every red node must be black. So those three reasons or those three rules govern everything. Why those rules? So this is once again my intuition for those rules. Maybe I'm completely mistaken, but if anybody knows better, and let me know in the chat. What I do know is the following, right? These three rules are there to guarantee the reason why red-black trees exist. So red-black trees exist as a way to balance a binary search tree. We all sort of know that. The question is, how do they do that? And they do that by guaranteeing that the longest path to a leaf node is at most, 2 times the shortest path to a leaf node. And so they're able to bound the amount of sort of traversals that you need to do by, I think it's like log and then 2 times n, something like that, right? So if you notice the rules of a red-black tree, especially the third rule, what ends up happening is the second rule tells you that in a red-black tree, things are going to have this sort of alternating fashion, right? First it's going to be black, then it's going to be red, then it's going to be black, then it's going to be red, and so on and so on. There are like cases where this doesn't happen, but like the gist of it is you want to alternate the colors as you go down. And with this rule, the rule number 3, saying that every single chain has the same number of black nodes, you're guaranteeing that independent of how short some given branch is, say I have some branch that's like 3 blacks in a row, right? Since the path to every leaf must have the same amount of black nodes, and I have a branch that is, you know, all 3 black, I know that the biggest branch that could exist has at most 6 nodes. Why? Because I know it has 3 blacks all the way to the leaf. And so the only thing I can do to elongate it is put reds in between. I cannot put blacks because then that breaks the third rule. I can just put reds in between. And that means I can just put at most 3 reds, right? One here, and then maybe one at the end. So that way you're saying like, oh, I know that the size of every single branch is bounded, right? I know this tree is not going to become a stick. It's going to maybe be a stick, but like I know exactly by how much. And it's not going to be by a huge amount. And so that is the reason why these rules are here, especially 3 and 1. And same for 2. Sorry, for 3 and 2. These 2 rules are there for that. And then the root and leaves are always black. They're precisely there to facilitate this. But you know, those are more there for the behavior, right? Yes, exactly. They're there to prevent the extreme left or right leaning, where you have a binary search tree where, like, you know, if I insert, maybe I insert 1 first, then I insert 3, so that would go to the right, then I insert 5, then I insert 8, and then I insert 10, right? This is a binary search tree, but the lookup, it's going to be O of n instead of O of log n, which is what the binary search tree is supposed to be. And so you want to prevent scenarios like this. And that the way red-black trees prevent it is by imposing those rules, so that you know that whatever happens, this sort of these stick-like things are not too long as to become a problem. And so when you detect that one of those sort of stick-like things becomes too long, like here, you detect that by saying, oh, we have broken the rules of the red-black tree. What do we need to do now? Right? Because now this path has 1, 2, 3. Actually, no, we didn't break it. We just fixed it, right? Maybe if we insert another black, it would be like, oh, we've broken the rules. Because to get to this leaf, we have 1, 2, 3, and 4 blacks. And to get to this leaf, we have 1, 2, and 3. So that breaks rule number 3. And so now we say, oh, how do we fix that? And then we rotate the tree, which actually makes things shorter, right? So, and so on and so on and so on. So all of these rules are there just to prevent that, to balance the tree precisely. And the reason for the rotations is, you know, you have to evaluate the cases sort of one by one, right? Case 0 is very simple. If you have a new node, if you have a new root, then you have to make it black, because the first rule of a red-black tree is the node is always black. So that's pretty simple. Case 1, where the new node's uncle is red, it means that if you have a red uncle and you're having a problem over here, you simply, there's not much you need to do, because if your uncle is red, it is not introducing a new black to the sequence or something like that. You yourself are also red, and thus you simply fix it by recoloring everything so that the blacks are distributed correctly in every sense. So yeah, each case just becomes a sort of analysis of like, oh, in this situation, how will we restore the properties? And then you have that, right? But yeah, that would be like very, very small and a little bit chopped explanation. But yeah, I don't know. With no context of what's happening, we were just talking about red-black trees, and like why they are the way they are. Yeah, I don't know. So, coming back to this, so we were taking a look at the tests we have to see whether or not the red-black tree is working, and we ran into an assertion issue, which is a bit worrying. Well, not a bit, very worrying. So I think if we just run this in the debugger, we'll be able to see which assertion failed. I think it's this one right here on line 74, which shouldn't be failing. Yeah, it shouldn't be failing. So we continue, we continue, we continue. Pa, 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 pa. We rotate. Yeah, and now we have an error. What is the error? So we have 5. Yeah, so all of these guys, they make sense, right? The problem is like, why is this assertion failing? So what does the vector tree, what does the vector tree look like? It looks like all of these things. So yeah, say the size of 0 should be 400 because it's 10 times 4. And then in the expected array, yeah, it should be 400, right? 400, then, oh, size 0. What? Why do we have a size 0 block? So 5 is the one that's supposed to be there, but it just has size 0. Huh? What's going on? Let's see what happens when we set the size of 5, which is indeed the first guy to pop up. Let's wait. So when we go into the heap, right, we are creating this block, and when we set the size of 5, so I want to know block size of 5, then we should see the size, but it does not. Oh, I guess it's BK size of MB. Yeah, 200, which is 50 times 40 times 4. So what happens? Why does it fail? Right? Because then if I do the block size of 5, after this, it's 200, right? And it's gonna be 200 all the way down, hopefully. So here, still 200, still 200, 200, 200, 200, 200. When we link them together, it is still 200, 200, 200, 200, 200, 200. We left rotate, it is still 200. And then when we convert it to a vector, boom, it like gets ruined. So is this an indication that there's something we're doing wrong? Yeah, 0, 0, 0. Yeah, we're basically, so there's something wrong with our red black tree to vector function. Let's see, what are we doing here? So we grab a node pointer result. We change all of its properties, which is fine. Then we wait for the red black tree to return whatever it has. Oh, I see what's going on. Okay. So yeah, this is a node pointer, so there's no need to do this. We just add the amount by which we need to the number of nodes we want to skip, not the size in bytes of the nodes we want to skip. Okay, perfect. Thankfully, it was just an error in the function and not an error in the actual red black tree implementation. Because if that was the case, it would be a sad day for all of us. No, assertion failed. The first assertion, literally. Oh no. Okay, so we insert into the red black tree this block called 150 times 4. And then we verify whether or not they're equal. Right? And the way we do that. Oh, dude, why are we comparing? Whoa. yeah, why is this a 7? I mean, a size. And then we just say vector tree dot size different from this. If you don't assert it, it cannot possibly fail. Okay. Do not follow this guy's advice. But yeah, no. Um, but yeah. Microsoft headquarters, you know. Anyways. Vector I dot size and then the expected one. And then we want to compare also the color. The color is important to us in this instance. Well, this would be more like an or. Or the colors differ. So expected instead of I dot color. Color. Perfect. And so now we should be able to compare colors too. And it should only go up to size. Shouldn't be invading memory that's not there. So let's recompile. There you go. And then let's run. No, guys. Please. Don't forget to put everything in uppercase. Yeah. See, line 92. What is line 92? This guy. So we insert. Huh? Oh, assertion failed. In function bk color. What? Oh, line 92 of mm.c. I imagine is the assert we have in the set color function. Where is it? Oh, there you go. Block member variables, bk set color. Then we have, yeah, we have an assert that we're not setting the color of a null block. But it seems like we're doing it somewhere in the program, which is really concerning. Why are we doing that? Oh, I think I know. Okay. So what happens is in the red black tree, right? When we work with rotations and all of that, we sometimes need to, I imagine, like recolor our sibling or recolor a parent and so on. The thing is to obtain the color, right? Remember that if, ooh, this is really important. This is really important. So over here in our memory file, right? Ooh. Yeah, there's something we didn't account for. Remember that the leaves are black. So we're supposed to return black whenever they give us a heap pointer, but we didn't account for that, right? Color needs to return this. And we didn't do this. Okay, so that's a bug in the translation. Never mind. I did translate wrong. I have failed all of you. Unfortunate. Okay, so we simply do this and we say, well, if block is a null heap pointer, then we return black. Otherwise, we return the actual value. Right? Hello? C++? Yeah, there you go. Okay, so that should give us what we need for the red black tree. Thank God we tested the red black tree. Okay. Assertion failed. Okay, this is one of the bad ones because we're failing an assertion of how the tree looks like, which means it's like not rotating correctly or not doing what it needs to do. So it failed on line 104. of, yeah, okay. So the tree no longer looks like 50, 10, 150, and 120. Why? Why? Did we translate the test correctly? You know, that may be. So 5, 1, 15, 12, yeah. Yes, we did. Oh no. Oh no. Okay. Are we doing the right thing? So 150, we inserted, then we insert 50, yes, which is the same as 5. Then we insert 10, which represents the 1, and then we insert 12. Hmm. Oh, yeah, this should be completely fine. So what is going on? What is going on? Are we sure that our equal function does the right thing? Yes, it does. Okay, let's introduce a breakpoint here to see what the vector says about the tree. So recompile, run it again just in case we ran stale. No. Okay. And let's see what the little guy says. So let's wait and wait and wait. Oh yeah, perfect. So you continue, we left rotate and do all of that. Okay. So I want to stop not on this line. I want to stop, let me get rid of all the breakpoints. I want to stop whenever we reach line 104, which is this assert. Only then do I want to inspect the red black tree function, yeah. So red black tree equals vector here. And let's go there. Perfect. So now we convert this to a vector and we pay attention to what it is that vector tree will store. So according to the program, the red black tree looks like this. Size 600. What? There is no node of size 600. What? Huh? Yeah, what's going on? Wait. If we take a look at expected 0, we see a node of size 200, a node of size 40, a node of size... There's no node of... Oh yeah, there is a node of size 600. But it is not at the root, which is a huge problem. So the node of size 600 would be 120 times 4, maybe? No. 150 times 4. So this guy, for some reason, 15 is still the root of the tree. Why is it the root of the tree? Oh, brother, this is really puzzling. Really puzzling. Yeah, it shouldn't be. It shouldn't be, which surprises me. Okay, what happens if we do rb_tree dot block? And we take a look at which block. So it's block number 0. Which is the ghost node, right? And then I want to take a look at what the left child of the ghost node is, so that we can know what the root is. And that gives us 2108, block 2108. So block 2108, what is its size? 600, yeah, so it's taking the wrong root. What's going on? Yeah, maybe it's not touching the root or something. I'm not sure why that would happen, because we... Okay, this is the annoying part of translating code. because it means that the error is somewhere in these lines. Yeah, it's gonna be a tedious thing to debug, but we have to. Okay, let's run with it. Let's run with it. So I'm gonna stop at every point of the way. I'm gonna stop here. And we'll see. Okay, continue. Perfect. So let's expand this. So we're inserting into the red black tree a new block. The red black tree should be completely empty by now. So these, I think it's going to be useful if we use our memory inspector. And for that reason, I'm going to move the camera a little up. There you go. Perfect. And I'm going to make it a little smaller. There we go. So let's take a look at the memory inspector and let's eliminate this. Add a new view for 0x1234567 CBF4 12345. That should take us, yes, that should take us to where the blocks live. So currently we have a ghost node, right? Because when we create the red black tree, actually let me start this from scratch. I want to see everything, including the creation of the red black tree. So let's add a new memory view. Oh, let's wait. New memory view. There you go. We see what the heap is. Perfect. New memory view to go to 0x 1 2 3 4 5 6 7 8 to f 4 1 1 2 3 4 5. Perfect. So everything is zeros. When we go here, oh, okay. Some of the information from the previous test is already there, but that shouldn't bother us because we create the red black tree, right? And I'm willing to say that when we create it, we set the left. We don't need to set the size, right? Because it should not be something we worry about. Okay. When we insert that new block, it's going to live somewhere. Somewhere. And it's pointing at position 3C08. That's like really far away. Yeah, over here. Right? No, 8, 3C. Yeah, it's living here. Why is it so far away? Anyways, so we continue. We don't need to take a look at that. Yes, okay. Arbitrary insert. We insert into the tree, whatever this is, then everything seems to be fine. 10 has absolutely no problem. The problem is when we insert 12. So let's take a look at what happens here. When we create the block, the size is 48 because 12 times 4. And everything is here. It's set up. Great. And then we continue. So now I want to step into the red black tree function. Perfect. Okay. So. We assert that it's free. We set everything to the default. And so now we should see current block, which is BK. So current block should have nothing. Yeah, there you go. Its color is red, everything is null, perfect. Let's just verify that. So if I access the parent of current, ooh, why is the parent of current 0? Oh, it's not current, it's new node. Yeah, it's null. And then same thing for its left child, should be null. And same thing for the right child, should also be null. Yes, okay. the color should be red too. So let's test that. Not test it, but like see it. Red. Okay. Yeah, so the ghost node is going to be whatever this guy is, which is the first block ever. It's fine. Then the current will be the root of the tree. And the root of the tree should return whatever the root is, which according to the previous state, it's 50. 50 times 4, right? So let's take a look at what cur is. bk size, and then cur. 50 times 4 should be 60. Sorry, 200, yeah, 200. I was gonna say 600 for some reason. Yeah, okay. The root is not a heap pointer, null heap pointer. So now we navigate down the tree until we find an insertion spot. Let's see if we get to the right place. So in the Excalibur, we can take a look at what the tree is supposed to look like. Over here. So I think I can close that. Perfect. The tree is supposed to be 50 at the top, 10 on the left, 150 at the right. So we can just reuse this drawing. 50 at the top. Right, so here. 50 at the top. Ooh, why is it so thick? There you go. 50 at the top. 10 on the left. Or like 100 or 40, whatever the multiplication is. And then 150 on the right. Which makes sense. This is a valid binary search tree. But each of them has different colors. It's black, and then these two are red. So keep this picture in mind as we go through the insertion process. Perfect. So now it's going to look for a point of insertion for 12 times 4, which is 48, right? If I remember correctly. Oh, dude, oh my God. That's the problem. We're inserting 12 times 4, but we're checking for 120 times 4. Of course it's gonna be different. Dude, and this is 130 times 4, and this is 170 times 4. And this is 190 times 4. Oh no, I forgot to change that. Okay, wait, at least it's not a correctness issue. Wait, that's pretty good, wait. Okay, I cannot believe. See, that's the problem with like having the sizes be forcefully 4-byte aligned. It's like really annoying. Okay, another failure in the same spot. What? Wait, did it not change? Wait, chat, is this real? Yeah, what's going on? So if we were to insert 120 in this tree, where would we go? Well, we go 50, 150, and then we insert it to the left of 150, right? We insert it to the left of 150, then it would be like 120. But this like breaks all the rules. So the tree, if I remember correctly, should look more like 120 becomes red, 150 and 10 become black, and the root is also black. So it should look something like this. So the traversal should be 50, 10, 150, 120, which is what we have, 50, 10, 150, 120. And so you're telling me there's an issue with that. Are we sure we recompiled? Yeah, the issue is in the same place. Okay, so there is something actually wrong. What that is unknown to us. So let's run it. There you go. Create the roadblock tree, that's fine. This first insertion works well. This also works well. This also works well. And then here is where things change. So we want to step into the create block function and then just return and step into, oh shoot, no. Okay, I missed it. I think I missed it. Oh wait, no, I didn't miss it. Sorry. My bad guys, sorry. Wait, no, I actually did miss it. Wait, what am I talking about? Let's run it. Let's get to the one we are interested in. We create this block, we continue, right? Oh, what the hell? Okay. We continue. We created the block, great. And then we step into the insertion process. So we take a look at whether or not it's free. We set its left, its right parent, the color, everything. The ghost node, we take a look at the root, which should be the 50, so it should be 200. Yes, the current size is 200. Then we skip this section, and then we try and look for a place. So the place we should end up should be 150, right? The left child of 150. So take a look at the current. The current is the 200. And our size, which is like 480, if I remember correctly, right? What is the size of the new node? It's 480. UK size of new node should be 480, yeah? So we are bigger than it, so we go to the right. So we should go to that else, yes. And we know that the current one does have a right child, and that right child is 150, right? So yeah, it does exist. So now we should be seeing current become 150 times 4, which is 600. Yes. Now we continue. And then we say, well, am I smaller than 600? Yes. So we step into here. And we take a look at whether or not current's left child is a null pointer, which it should be. So we enter this if, yes. And then we link the two together, and then we break. Perfect. Now the color of the current one, which is 150, before the whole thing happened was red. So this thing should mark red and thus skip. Yes, perfect. And now what we do is we say, well, while we haven't reached the ghost node, we go, oh wait, Stephen LB, thank you very much for joining. Yo, hello. I remember you from yesterday. Yeah, currently we're debugging something. There's something in a red black tree implementation, like the translation we did, that is wrong, and we don't know what it is. So it is, it's a little bit of an issue. So let's take a look at the red black tree of how it was before the insertion. It was 10 red, 150 red also, right? 150. And then 50 was the only one that was black. So 50. There you go. And so now we're going to see what the issue is. So when we insert 120, we insert it over here. So you now see the issue because there's two reds colliding with each other. And the case we should apply is the case where your uncle is red, which is case number 1, if I remember correctly. So let's see. This case does not apply to us. There are problems, so we shouldn't enter this if. And we should enter case 1. Yes. So now we set the color of the grandpa to be red. Then the color of the uncle to be black. And the color to the parent to be black. So now what that does is it makes both of these black, 150 and all of that, right? 150, blah, 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 and then 10. And it makes the root red, right? It makes 50 be red. So now there's a problem because the rules say that the root should always be black. And so we go up the tree. Now, the new node should be, its size should be 600 because we move up to 150. And then the parent of the current should be 50, so its size should be 200. Okay, yes. And then this size should change to 200. Yes, okay. And so now we say, well, there's not much else, there's nothing else to look at, right? Ooh, I think this may be the issue. Yeah, this is the issue. Is it though? Wait, let me see. In our original red black tree code, did we have, wait, where is it? Oh, it's here. We should have had a continue over here, a continue. So let me take a look at, right, because it's like, oh, right, you satisfied this case, so the continue, it's like, ignore the other cases, those don't apply to us, let's reevaluate everything. Because now the current, it's going to be the root, right? And new node, it's going to be 150. So if we continue, we take a look at like, 150's uncle, assuming that these previous two cases were not the ones that applied to it. And so now we mess everything up. I think that's the reason why everything is failing. So please tell me we have a continue on case 1. Yes, we do. Yes, we do. Okay. Sneaky continue. Dude, I cannot believe I forgot to write that down. Oh no. And that messed up everything. Okay. I think it's going to be more efficient to, since we know the implementation of the right works, just read the code again and make sure that I didn't make any more translation mistakes. Because let's see. Case 1, we linked them together. Whoa. Whoa. What's going on? Oh, this is remove. Okay. This is, there you go. This is the thing we're looking for, the insert. C. Yo, this language made me successful and I owe a lot to it. Yo, pretty good. In what sense do you appreciate C? Like, when you say it made you successful, like, did it make you learn a lot of programming? Did you create a company that you see? What is sort of the motivation behind it? In the meantime, while you type, let's just keep reading the code. So here we set the color and then we break. Yes. Here we take a new node and then the current parent and then continue. Yes. Learn, and it is the language that runs my business. Damn! Wow. Wait. So both of them. That's crazy. Pretty good. Pretty good. What is your business about? Like, is it a software business? Is it a different type of business? And how do you use C? Do you use it for like very performance critical code? Is it reliability? No. Yeah. Let's see. PK parent. Because currently, I mean, as I've mentioned multiple times, this is my first introduction, like proper serious introduction to C, because I always usually use C++. So I'm glad to know that it's an important language to you, because then it means we're on the right path. But yeah, let's see. Case 2. We're doing everything right. TMP. Yes, we continue. The line direction. If line direction set color to red and then set the color to black. And then we break. Okay, that should be everything. And we should be able to run the test and find 0 assertion errors. In an ideal world, this thing should not fail. Yo, let's go. Okay, we passed the insertion test. The tree rotates the way it should. Everything happens beautifully. API business. Interesting. PubNub. C written the globally distributed message boss. Eventually consistent. High replication. Damn. Wait, that's pretty cool. That's pretty cool. Wait, let's take a look. What does PubNub do? PubNub. Will it appear on Google if I look at it? Um, build, manage, and optimize real-time apps at scale. Is it this one? Yes. Okay, that's it. Yo, perfect. Wait, let's take a look. Live stream chats, in-app coaches for. Oh, wait. So I want to know what exactly the company does. PubNub has the real-time platform behind engaging apps, a chat, live updates, and in-app interactivity with ultra-low latency APIs. Oh, I see. Wait, so it do sort of um is it just specialized in giving very performant sort of memory transmission channels or like things, right? So I just see the example. So gaming could be like, have the correct um like what's the name? uh the channel to transmit all of the events that are happening from the player's computer, and then da 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 da, and so on and so on. If it's a call center, if it's transport and delivery, okay. I imagine it's something like that. Just correct me if I'm wrong. Yeah, transmitted the data transmission. Oh, what the hell? You're like supremely successful. Damn. Wait, congratulations. This seems very good. And um wait. Can I share this with my team, your VOD? I mean, sure. Yeah, I'm not sure why you would want to, but yeah. Definitely. You say it's distributed message bus. So basically C is the core of the business, right? Because if it is the distributed message bus, that is quite literally what you do. It's eventually consistent with high replication. Pretty good. What is the underlying sort of protocol that you followed for it? Did you use like Raft, Paxos, or I mean, it's between Raft and Paxos, usually the ones people use for like replicate. Well, I guess you didn't use Paxos because it's eventually consistent. So Paxos is not. Paxos is immediately consistent, so it's linearizable. So never mind. Um, so neither Paxos nor Raft. Something like Amazon Dynamo's model, maybe, is what I'm thinking of. The core message bus, and we are rewriting to Rust. This seems to be the a very what's the name? A common trope that's taking place in the software world. Yeah, this is why I want to learn Rust, right? Because it seems like a language that everyone is um sort of saying it performs the same as C, and it also gives you the benefit of having no memory issues with the use after free or like double, etc. So yeah, we're gonna learn Rust eventually in the stream. We'll see, but dude, absolutely amazing. Like Ticketmaster and everything. It's good data, your feedback. Seeing an engineer like yourself review and understand the tech, very useful. We use TCP and high replication, copy events to many separate systems. I see. Sir, every time I see Rust code, I feel like the devs wanted to use every character. I see. Wow. Wait, this is pretty good. Congratulations. Wait, can we take a look? Wait, oh, we have even documentation and everything. Um, to support multiple languages. I see. Start here. 3 keys is for the free tier. Is okay. We get the SDK. Oh, you have it for all of these languages. Oh no, there's no C. I mean that's okay, I suppose. Well, I guess the API, right? Um, but yeah. Huh. So I want to take a look at file sharing. So, oh, I guess this is just the description of the API rather than the. Oh, you have C. Okay, like maybe not in the SDK? Because I see JavaScript, Swift, Android, Dart, Kotlin, C Sharp, Python, REST API, and then chat. Like I imagine it supports C, maybe through the REST API or the chat. Or maybe I'm not understanding correctly. We'll see. Oh, it looks so cool. It's like, the JavaScript one, Node.js, Swift. So in Python, yo, pretty cool. So this is the SDK I meant. So probably we all supported SDKs is a small link on the SDK page. Oh, okay. So if I take a look at core SDKs, oh yeah, okay. These are more. These are the most popular. Yeah, I imagine nobody will want to do this in C. Uh oh, okay, we have the POSIX C. Okay, perfect. Approved. um yeah, this is bigger than like than it seems, right? Because people usually think like, oh yeah, you just need to transmit messages. It's not that simple. It's absolutely wow. This is incredible. 800 million devices, 200 plus customers. So this is like a huge company. Awesome. Dude, imagine having like it's like we're just some random stream coding some memory allocator, and then like soon to be the soon to be richest man in the world just joins the stream. It's, but no, this is great. Dude, keep it up. I mean, eventually, everybody's dream is to reach a state like this. To have an idea for a company so you can be independent and build software that you love. So you're definitely leading the dream. I hope. No, like you never know if the company, maybe there's some problems or anything. I hope not. But yeah, this is awesome. Pretty good. Crazy. And for now, before we get to obtain the $1 million idea, we need to continue with our memory allocator. It is, it is a path. It is a path. Brick by brick, every day, eventually, the more we learn, the more information we gather. And rather than having, a specific goal, we're just here to learn. And eventually, people, eventually, remember this. If you don't give up, there is by definition no way to fail. Because you never give up. So let's continue. Let's learn. Eventually, the golden hour will arrive for us. So, thank you for spending time reviewing. Oh no, yeah, no worries. I mean, usually when people like share stuff in the chat, I like to take a look at what they're talking about. It is one of the advantages of having like a little community, because then I know that very big streamers in like maybe they don't have the time to look at those things or like stuff like that. So yeah, I mean, it's something I like to take a look at it. And with I didn't know there existed, for example, other versions controls different to Git. I kind of knew, but yeah, and then we did like an entire exploration on those. We're also looking at keyboards to buy. Because I have a keyboard, a mechanical keyboard, and then people were like, "Oh, there's like better keyboards out there." So we were looking at keyboards and stuff. So yeah, sometimes we just deviate and take a look at stuff. Plus, it is our moment of celebration because we got a success and then a glasses happy face in the test, which means we did right. We did everything well, so we needed to take a break too. Also, it's kind of, it's kind of, I don't know. It's very fun and interesting to see that. Um, I mean, I'm not sure why why you would thank me for reviewing, right? Like, I'm just a random college kid, uh, 20 years old, and the company seems if anything, you already have a measure of success in the sense that you know everything works okay. So it's very humble to say like, oh, thank you for reviewing. When, well, really, we're not. we we don't have as much expertise, perhaps, but yeah, thank you. And whoever wants to bring maybe stuff they're doing to the stream or something like that, feel free. I know that Fanbeer has been updating us with the whole Wayland Wayland thing with the creation of your custom UI Fanbeer. So yeah, it's very interesting. Very interesting. I swear every time I find a lib that I need for a project, it always has a random build system that it just makes you annihilate you before you can ever use it. Interesting. I mean, does that happen with C? Because I know that for C, CMake is very much standardized. Um, and like make files and stuff, but especially GNU and similar. Interesting, interesting. I see. Yeah, I guess I don't have enough experience with C to pick a side since everything I just do it in C++. Um, yeah, I mean, oof. Okay. We have tested. CMake is not at all standard for the average older. Oh, okay. Well, yeah, I guess CMake is newer. Yeah, so for older libraries, it becomes worse. Okay, I see. Yeah, well, because here, guys, let's see. Hear me out. We're testing the insertion, right? We already tested it. It printed success. So guess what we need to do now? We need to test find. Okay, we're hopefully going to finish all of the tests today because we're done with insert. So we have all of the we have the API we need. Uh, by that I mean like the syntax on how the test looks in C. So what we're gonna do is we're gonna say, well, let's create a new redback tree by calling the create redback tree function. And then we're going to insert a bunch of stuff. So arbitrary insert, and I think we can just copy all of this and paste it here and simply modify the way things are written. So what we're going to do is we're going to do arbitrary insert. Insert where? Well, insert inside our redback tree a create node. Oh, wait, no. I think it was a size node. Yeah. Wait, no, right? Wait, how did we initialize the create block? There you go, create block. Sorry about that. Create block of size, whatever the size that was given, and that multiplied by well, multiplied by 10, so we got a 0, and then by 4. Perfect. Okay, so we have them all. And what we need to do is we need to check exact matches, as the comment says here. It's even worse in my case when I'm trying to port them to a non-supported OS. A non-supported like the library doesn't support that OS. Okay, I see. I thought you were saying like you had your own obscure OS that you built like 20 years ago, and we're like trying to port everything to it. But yeah, okay, no, that's more reasonable. Yeah, take a look at this. So int nums is equal to that. Perfect. So we have 150 times 4, 50 times 4, 10 times 4, 120 times 4, 130 times 4, 170 times 4, whoa, brother, hi. Okay, there you go. 190 times full, and then 210 times full. Oh, wait, so you're actually okay. I'm sorry. Wait, I didn't mean to. Yeah. I was meaning that I thought it would be a crazy idea to port it to like your own OS. Because it'd be crazy to have your own OS, but it seems like you do, which is pretty impressive actually. Damn. 1, 2, 3, 4, 5, 6, 7, 8. Is it based on something specifically? Like, do you just use the Unix POSIX standard, sorry? Or is it just, you know, can you just design it be as specific? Whoa, what happened? What did I just do? Oh, there you go. Perfect. 170. Yeah, okay. So then we do this, smaller than 8, and then we do plus plus I. So we do nums and then I. Oh, not I, sorry, A. And then we assert that whatever we find, arbitrary find, for whatever that number is, which would be nums inside of I, then that thing, it gives us a block. So we should be able to say bk size is equal to whatever nums I is. Perfect. So arbitrary find, oh yeah, we need to pass through the regulatory. Yeah, and that way the test does exactly the same thing. Perfect. Okay, we return true if everything goes well. And then we're gonna check if it returns the lower bound when we have not an exact match. Right? So here we copy all of this, and then instead of having the assert, what we do is we say, we grab all of the lines, we find, so arbitrary find, and then provide the red black tree that we want, and then the size. But remember, all of these sizes need to be multiplied by 10, so another 0, and then multiplied by 4. Right? Perfect. And so rather than accessing the data, we need to access the size. So we find the size of this guy. Oh, for some reason we missed that one. BK size. There you go. And then we close it here. Perfect. And then rather than a null pointer, it should be a null heap pointer. Oh, there's a reason why we missed it. Yeah, this is supposed to be a null heap pointer. Perfect. So all of these numbers should also be, yeah, so 120 times 4, and 50 times 4, 150 times 4, 10 times 4, 90 times 4. If you're wondering why am I multiplying the numbers by 10 and then by 4, it's because we have the restriction that every block is at least 16 bytes of size. So for example, for number 5, that's not bigger than 16. So I just multiply by 10 to make things simple, to keep like the same numbers, just satisfy that constraint. And then multiply by 4 because all sizes must be at least 4 byte aligned so that we can use the last 2 bits. And so that's why you see me multiply by 4 everywhere. And then after that, we return true. Okay, perfect. So I think we're fine. I think if we recompile this one, I'm very sure it's going to succeed on the first try. Let's go. Oh, wait, never mind. We need to call the test flight. Red herring, people. Let's see, recompile, and then we execute. Success. Perfect. Yo, find works. Find works, awesome. Let me read the chat. Okay, so I'm trying to put, yeah. Well, is this a pseudo working TTY LOL? And yeah, POSIX. I am not making my own standard. Sorry, enough. Yeah, missing like 90% of all stuff. Wait, but that's still pretty cool. That's still pretty cool. Building at least parts of our OS. It's something that's very interesting. I think one of my favorite projects was creating a thread library. I created a thread library from scratch. I also made a virtual memory pager from scratch, which was also very interesting. And yeah, every time, like, the anything related to low level systems, it's extremely interesting. If only every code worked first time every time. Yeah. If only, wouldn't it be nice if we could? But yeah. Um, Finally, we're gonna add the tests for remove. So what we're gonna do is we're gonna have a red black tree, or a tree. Then we're gonna say, create my red black tree, please. Thank you. And now we're going to port all of this. So this one's also going to be a little annoying because we have a lot of things. So yeah, so I think we just need to create, I think these are the exact same blocks, right? Yes, they are. So we can simply copy this and then paste it over here. There you go. Awesome. And now we need to perform the removals. And the best part, user space programs take the whole OS down with them if they fault. Yeah. It's like really, really, critical. Like, you have to be extremely careful with what's going on. Because yeah, if you have a normal program, then it crashes. Like, the OS knows how to handle it. But if the OS itself or anything in it fails, it's like absolute chaos. So yeah, let's see. Remove from the red black tree. What do we want to remove? What a great question. So I think we're gonna have to give them the names. Yeah. Yes. I think because we need to reference them later. So, ooh. Well, okay, that's fine. We can go out here and then put this, and then we can say, keep pointer t 15 equals. I guess we can just do this for every single one of them, where we do a keep pointer that's going to be returned, and then we provide to it an x for the name. 15. This one's 5. 5, 1, 12. Wait, 12. 12, 13. Ooh, 13, 17, 19, and then 21. Perfect. And now we insert all of them into the red black tree. So we're gonna do arbitrary insert, and then all of them in that exact order. So we're gonna grab, I'm actually gonna grab this entire set of lines. And oh wait, at least it allows me to debug in a simpler way when trying to guess what's segfaulted. Yeah. Pretty good. Let's see. And so what we want to do is we want to move here, delete. Then we arbitrarily insert into the red black tree and then pass in the 15 variable. There you go. And then fix these two guys. Choop, choop. Perfect. We inserted. And now that we inserted, we need to see that the removals are working correctly. So we're going to grab all of this code that we have for removals, paste it over here. Finally, return true if we don't die along the way. And let's see. So arbitrary remove is going to change its syntax to be arbitrary remove, and then we need to pass in the arbitrary. Perfect. Okay. Now we say, okay, this, we need to pass just the red black tree itself. Perfect. Here, we simply need to translate this into the language that we had, which is CS node, and then whatever this guy is. So I guess the best way to do it would be replacing all of these instances where we have brackets and then color by just having, let's see, CS node of black, and then we erase the keys and put in the parentheses instead. Perfect. So that should work. And now we just need to type what this is. So this would be a node of, well, let's see, 1, 2, 3, 4, 5, 6, 7, 8. Node of 8. And that should be everything. Oh, wait, no. And then we need to add the size here, 8. That should be everything. Yay, okay, perfect. So now this is gonna be a node of 7. Oh, a node of 6, what? Wait, how many are there here? 1, 2, 3, 4, 5, 6, 7. Oh, sorry about that. Actually 7. 6, and then this one should be a 6. This one should be node 5, and it should include a 5 over here. This one should be node 4, and it should include a 4 over here. This one should be node 3. You get the point, right? Node 3, and then 3. Finally, we are left with only 2. Left with 1. Oh, we forgot to change this one. That's interesting. CS node black 21. There you go. Perfect. Then we remove the last one, and so we're left with this assert, where we take the root of the red black tree and then verify that it is a null heap pointer. Awesome. That's all. And now we need to be very careful. Remember, we need to change all of these numbers. All of these numbers. Do not make the same mistake as before, where we had all of these. Ooh, the batteries of my microphone are gonna die. Well, not my microphone, my AirPods, which I think I use as microphone. CS node, right? We have it here, and so we're gonna jump. Oh, sorry, no, I meant select all instances. Oh shoot, no, not those. Wait, only the ones that are inside remove. So this guy, and then we go da 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 1. Okay, so we move to wherever the number is, which is here, and then we add a 0 and multiply by 4. Perfect. Okay, I think that's fine. I think this is it. Is this it? Oh, only one way to know, I suppose. Let's compile and let's run it. Are we going to see a success? Put your guesses in the chat and success. Yay. Oh, wait, no. Sorry, I always forget. We need to include the test to be executed. Recompile. There you go. And now we run it. Success! Yo, perfect. Everything works. Everything works. Our red black tree is indeed correct. Yay. All right. One thing I want, last thing. I swear. We need to test the right rotation. Wait, because I included the test for the left rotation, but not for the right. Yeah, we immediately started inserting left. Okay, we're gonna do this quick like the thunder. These will all be heap pointers, and they will be equal to what? So, well, this would be equal to create block. And so we need to know the size of the block. So we just pass that and nothing else. Yes, every single one of them needs to be multiplied by 10 and by, ooh, what was that? Multiply by 10 and by 4. There we go. And so now we can link them together. The thing is, we don't want these ampersands, so we erase them all. Sorry. This, 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 this. And this is not called link, it's called t-link. Perfect. Now for the result, we do the same thing that left rotation did, which is store the heap pointer. We store the heap pointer instead. Heap pointer t to 10. And then we do the exact same thing. So now this is just like the exact same. I'm just gonna copy it. And then, so how many do we have? We have 1, 2, 3, 4, 5, 6. No, 1, 2, 3, 4, 5, 6, 7. Okay, 7. Which means that we can just do this, and the expected array is a little bit different. It's 5, so 50 times, okay, so 20, 100, 80, 60, 90, 120. Yeah, perfect. Perfect. So now we can get rid of the rest. Okay, perfect. That should be the code for testing the right rotation. And we cannot forget to include it into our test suite. So now we do test, then we try and test the right rotation. Then we reset, let's recompile, and then let's run the test. Success! Yo, let's go. Okay, so now we can be a little bit more certain that our implementation of the red-black trees is indeed correct. This deserves, oh shoot, wait, have I been in the wrong branch all this time? Yeah. Oh no, okay. How do we do this? So, what are some of the changes we've introduced? I want to see if I can just put them in a different comment. Oh no, we changed the structure and everything. Okay, that's fine. Let's just get at everything and then comment this as test. Add red like 3 tests. And push. Perfect. Okay, that sounds awesome. So now we have the test for the red black tree. We can be a little bit more certain that that is actually working and that we didn't make any mistakes while copying it over. Thankfully, we did it because we did have a mistake, which we couldn't really notice until we actually started writing the test and we realized that the parent, when you set it to null, it would actually not be null. It would be like 1 less than null. Because if you were to have set the color at that time, it would have overridden the value that was already there. Like, it was a crazy bug. But it's okay. All right. So let me take a look at something. Just for one minute. 1 minute. Give me 1 minute. This is 2. Let me see. Okay, I think I'm good. Justus Flugel. Hello, welcome to the stream. Yeah, we're coding a memory allocator from scratch, as the title says. We have already implemented a lot of stuff. We have already implemented malloc, our own version of malloc, our own version of free also. And we were just testing the red-black tree implementation that we have, just because we're using red-black trees to store the free blocks. What kind of allocator? It's just gonna follow a best fit policy, right? So it's gonna be a normal allocator that follows best fit. So when the user provides a request, you're just gonna find the block that fits the request the best and then give it back to the user. Yeah, we're not compacting or anything of that sort. Mainly because, in C and C++, it's like very difficult to create a compacting heap, although it's possible. Because like ideally you want it to have the same interface as malloc. If you want that thing to be compacting, then I'm not sure how you would change it to be, because if you return a pointer, then you cannot compact, because you cannot move things around memory. Maybe I'm completely wrong, but yeah. I'm currently making a mess with macros in C. Why? Wait, what's going on? What are you doing? Tell us. In the meantime, we're going to, I guess, now that we have the tests for the red black tree, think 300 macros in a 900 like file generating what? What? Brother, no. Dude, what are you doing? What? 1/3 of your entire lines of code is macros. Um, um, Not an expert, but that may be a symptom that you need to reduce your macros. Maybe. I don't know. But yeah, I mean, depends on your. Yeah, what the hell are you doing? Obfuscated code. I mean, maybe you have a reason. Let us know, because that is a little unusual. Like, what? It's 2077. You still using C? Hello, G Suits. Welcome to the chat for the first time. Yes, we're still vibing with C. um, yeah, I feel it's a very pretty language, right? I'm used to C++, but C is like it doesn't have most of the problems that C++ has, where C++ like has a bunch of stuff, so you don't really know what it's trying to be. C is more simple, um, which despite being a little, sometimes you have to be a little more verbose for some things. It's like better as you get used to it. And yeah, generating packet serializers and deserializers from X macro definitions. I should probably use an external code gen tool, maybe. 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 But yeah, I mean, yeah. So, ah, anyways. So what do we need to do here? So we have all of this stuff with. So we also have some tests for both free. The problem is that these tests are not really automatic. So that's what we're going to. Pretty sure you could have done operator overloading in C with some crazy macros, by the way. Like, do you mean for the compactness, for the heap compacting? Because that's like what I imagine, right? If you have some sort of operator, but if you have some sort of operator overloading, then maybe you can get away with it. So maybe in C++, but in C that doesn't seem that possible. Also, implementing operator overloading with macros, it's absolutely insane. Um, a Wireshark dissector. What? Brother, are you working for for like NASA or something? Like these are very specific things, right? Like why are you using Wireshark? Just to test whether or not the packets are being sent? See, I hear Wireshark and for some reason I think like, oh, hackers. But it's not necessarily, right? Um yeah, I imagined, yeah, debugging for the packets. Okay. And yeah. Um. Whoa, 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 whoa. All right, guys. I think it's yeah. So we've been testing our our program and everything, right? It seems like it works. We have these two little tests for free that are not automatic. Right? It's very important to notice that they're not automatic. They are just us taking a look at memory and seeing that the bytes are in the right place. So it is a little bit of a naive approach. We need to implement sort of automatic tests for free. The same thing for malloc. And since verifying byte for byte that the output is correct is equivalent to implementing the entire thing, I think we're gonna test it more behaviorally. Right? So we're gonna do all sorts of stuff. Um, yeah. So let's see, using an SDR to capture the packets and then sending them to Wireshark. I see. Pretty good. Right now, we find ourselves in an interesting position because we have finished malloc, we have finished free, and we have sort of a decent degree of confidence, right? A decent degree of confidence because we have tested, we've seen that the bytes work correctly, that everything is fine. We have not tested it thoroughly though, so there may be some sort of edge case. But we could write our first program using our allocator. Or we could start implementing realloc, which I think is actually what we should do, because we shouldn't leave realloc aside. Yeah. So I think I'm gonna check out a main, right? Oh, mm test. Okay, do that dot comment dash m. I think I just wanna say test free. Add execute test free one. Reset. Then we're gonna check out main, and we're going to merge with feed free. Perfect. So now everything is in one branch. And what I want to do is I want to check out a new branch that's going to be called feed realloc. Perfect. Yay. Okay, so now we can implement realloc. I'm going to make an exception. I'm going to make an exception. Today, let's end the stream at 11. Okay, at 11 a.m. Usually it ends at 10. I know, but this is, we're nearing the end and it's feeling very exciting. So let's do that, okay? Give me 1 second though to get some frosted flakes because I wanna eat some frosted flakes. Gonna grab some. Gonna grab a spoon. Bada bada bam bam bam. Bada bada bam bam bam. There you go. Time to eat the frosted flakes. The frosted flakes, best frosted flakes in the world. Something. Um, there you go. I have some here. I'm a frosted flakes addict. And yeah, so I am so sorry, guys. You are going to wait. Okay, let's see. Realloc FTW. What does FTW mean? FTW. What does that mean? Let's FTW in texting meaning. In texting only chat, for the win, it's an informal expression used to show excitement, support, or approval for something great. Used to express something awesome, a great trace of victory. So tackles FTW. Oh, like the world. Okay. An older, rebellious slang term, occasionally used in alternative or punk. Coffee FDW this morning. As in, coffee is the best choice right now. We won the game, FTW, an expression of victory. Ooh, okay, okay. I agree. Realloc FTW. Yeah. Realloc for the win. Let's keep reading. Any plans for what's next after the allocator? What a great question. The plans are not set. I can tell you that much. Like, I don't have something that I'm saying, yes, this, and we're going to do this, right? So if you guys have some ideas of things that you would like to see, I'll take a look and I see if I like something that maybe you guys suggest, and then we can do that. I'm currently thinking. So one of the projects I've been thinking on is to learn Rust, right? So I want to learn Rust, want to learn about it, and there is something that I find very intriguing and like fascinating about like the concept behind blockchain systems and like cryptocurrency. I don't like the world of the cryptoverse and cryptocurrency. I don't think I would ever invest in like something similar, a bunch of speculation and stuff. So I'm not talking about that. I'm talking about the original Satoshi Nakamoto paper on how proof of work works, how the blocks are supposed to be together, all of the encryption that goes behind it. It seems like an interesting thing to me, right? Like how you end up creating a secure system without trusting basically any of the components. um, so it seems like an interesting thing, right? I'm not set on it. We can look at something different for sure. But it is sort of the idea that's ringing in my mind because it's also something like that to me seems, maybe the like it is low level systems and well in a sense, in the sense that like creating an entire such system from scratch, right? Or at least like a toy example of a blockchain and like all of the things involved in it from scratch is not something that is like low level from the perspective of, say, an operating system, as we're writing this allocator or a virtual memory pager or a thread library. It's more like, something that seems rather more modern, like weirdly modern, and I don't know, it just catches my eye. But let's see. Let me know what you guys think. Maybe you're like, nah, that's a horrible idea for a project, and so maybe we look at something else. But yeah. Also, I have some macros that are pretty cursed and use recursive macros. Brother. Okay. The moment somebody says recursive macro, stop reading. Stop reading. Okay, macros that call themselves, well, using some tricks to defer any evil stuff multiple times to trick the preprocessor into doing it. No, please don't do it. Compiler is gonna go up at one point. Yeah, for the win. Yeah, sorry. Not the second winning. Make a Rust binding for the allocator. I hadn't seen the second meaning. Okay, Rust. I mainly do Rust dev. I forced to work with C this time though. An example of a packet definition I use the macros for to turn into serializer and deserializer code. Wait, let's take a look at this. What is this that you're talking about? Oh, V. No, I meant Control V. Um, Damn. Wait, this is like actual code, just like macro language. Wait, why specifically macros? Right? Like why are you using macros specifically, right? Because this seems like something that should be completely possible through just the use of the language, right? Through C. So why why are we like coding in macros? That seems a little annoying. Like you must have a reason, right? Nobody willingly looks at this and it's like, yo, this is the perfect thing. You know what? Well, it generates multiple strings from it. I mean, yeah, but interesting. Okay, okay. Hmm. Okay. Compile time 2 decades. No, yeah, kind of. Like that's what that's what intrigues me, right? Because you're gonna have like compile times that are severe. Actually, no. Oh, okay. Interesting. All right, all right, all right, people. We have basically 30 minutes to implement realloc. We gotta lock in. Random Hacker 89, welcome to the chat. Let's see, it's your first time here. So yeah, welcome. Have you tried Odin? No, I have not tried Odin. Um, I've heard of it though. I've heard of it. Um, but yeah, it is a goal to sort of learn and look at it. I feel it's a little bit of more like a long-term goal. It is a little farther into the future. I feel like I first want to learn Rust. So Rust and then take a look at Zig and then Odin after that. I think that's the trinity of languages in that order. Um 280 milliseconds plus or minus negative. Oh, whoa. That's pretty good. Also, wait, I forgot. Wait. Um Whoa, we have a whoa, thank you ZXCV256 for following the Lumen too. Thank you for following Raj Codes. Thank you for following Stephen LV for the raid and also for following. And Cretin2303 followed 36 minutes ago. Thank you so much. I hadn't been seeing the screen. And then Ratchester, thank you for the follow. Yo, let's go. Guys, we're going. Wait, oh my god, wait! I think we surpassed. Wait, Stephen LD was the follower number 100. Yo, guys, we have 100 followers. How crazy is that? A week ago, we had like 20 or like 16. Um, that's absolutely insane. Hmm. Hmm. Let's see. If you learn Rust, feel free to ask me stuff because I know Rust pretty well. Yo, let's go. Test it with high. Oh, okay, I see. Yeah, of course. I mean, I'll rely on you guys for a lot of C stuff where I'm like, wait, is this a C++ construct or is this also valid in C? So I guess with Rust is going to be the same. Um, yeah. Mm, 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 mm. Best creeper test. Yo, thank you for following it. Yeah, you've been really active in the chat, so yeah. Do you know the restrict keyboard? No. What? Like in C? Oh, what does this do? What the hell? In C. Wouldn't it be nice if we knew? Um, it's a type qualifier that can be applied to a pointer to hint to the compiler that for the lifetime of that pointer, No other pointer will be used to access the same pointed to object. Whoa, 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 whoa. Interesting. Well, now we know. Now we know. Perfect. Oh, it doesn't exist in the C++ standard? Oh. I see. One of the few things in C that doesn't. Yeah. I'm surprised because I thought that C++ was supposed to have full backwards compatibility with C. Seems that's not the case. All right. Let's see. 30 minutes. 30 minutes to implement realloc. People, put on your seatbelt. You know, accommodate yourself in your chair so that you're comfortable because the Armageddon starts right now. Okay, so what do we need to do for realloc? Whenever somebody needs to reallocate whatever they have in memory, we could have a naive approach where we free whatever they have and then just, well, we allocate some other block and then write the stuff there. Okay? That would be the naive approach. But there is a sort of optimization that we can perform. And it's what happens if from the block I want to realloc, it has a neighbor that's free. In that case, I would save all of the overhead that comes from copying the data and could simply just expand the thing, right? So that seems like a good thing to do. And it's an optimization that's gonna make the writing of realloc a little bit more interesting. Are there any other optimizations or things we need to think about? So currently what I'm sort of, what I envision is a situation where, let me take a look at our blocks. There you go. A situation where this block has a bunch of data in it, right? Let me make this more, yeah, there you go. This block has a bunch of data in it. And then the user calls realloc, right? And when they call realloc, they specify the new size, if I remember correctly, yeah. And thus, if that size is bigger than the current size, then we try to expand to the next node if that node is free, right? Otherwise, we default to the, free and then allocate some other block and copy all the data, right? There is nonetheless a problem, I would say. The problem is, I'm thinking of edge cases, and I think this one is an edge case that's going to make things interesting. Picture these two blocks, right? Suppose that data is present in this block. And now the user calls realloc to try and reallocate this block to something that is 2 blocks wide. Do we have 2 blocks? Yes, right? First thing we do is we copy the data to this one, and then we expand this one to occupy this one too. The problem is going to be that, initially our memory allocator is not going to see that the space is available because it only sees that there's one that's free, right? It doesn't see that after the realloc executes, you're gonna have 2 of them free and then you can copy the data. So that is an edge case because if we free this block, then all of the metadata, it's going to be reinstated, right? And so it's gonna delete part of the user data, leaving only the extra block. So we need to figure out what to do in that case. Maybe we need to do it a little bit more manually. So those are the three cases, right? The first case is we have a free neighbor, and thus we decide to merge with it. Right? Yeah, like clawless with it. The second case is ignoring the toRealloc block, or like, sorry, including the toRealloc block. There's enough space. Okay? There's enough space. No space, or like not enough otherwise. So that's the situation I was describing. And then number three should be just usual. In that case, just free, or like malloc somewhere else, somewhere else, then free. Okay? Perfect. So those are the three cases we need to treat, it seems. Okay. Perfect. So now, if we go here, and we have those three cases in mind, which I'm gonna copy over to the code here in like a little comment. There you go. Having this in mind, oh, let me read the chat. Give me a second. Try to stay on the same NUMA node. Can you realloc to a smaller size? Yes. Yes, that is the other case. Yeah, great observation. That is the other case that we need to shrinking. But for shrinking, it's gonna be a little simpler. Simply, create new free node if worth it. Okay. Because of shrinking, yeah. And vectors and so on, yes. Also, if you consider the current block is free during the search, you need to be careful with overlapping copies to do them in the correct order. Like if you 1.5 the size of a 2-block allocation and append a preceding block, you need to make sure to copy the blocks in the correct order. Otherwise, you destroy data. Yeah, exactly. So that is why we need to be so careful with realloc, and why I think realloc is not a piece of cake. Oh, Calicule, yo, hello. Yeah, but we finished malloc, we finished free, and now the only thing we have left is realloc. We have tested them both very minimally, but tested to a degree of confidence that we're like, oh, okay, this is working kind of fine. So yeah, we have realloc for now. Do you support calloc? We can create a calloc, right? I just had the scaffolding for these three because they're like the main ones. So yeah. So you grew mustache during my so I don't know about is it really mustache? Yeah, it kind of is. I don't know. I've I like have never let my mustache, if you can even call it that, grow. So I wanted to try and see. Like, what would happen? So, but yeah, it's basically just a shadow of this point because it's only been like 1 week. But yeah. So realloc. But first, a spoonful of frosted flakes. All right. So important. Assume we are augmenting size. Okay? Assume we're expanding. I feel that's better. Expanding. So we're provided a pointer by the user. What we're going to do is we're going to calculate what block that is. So we're going to grab the low end of the heap, and we're going to change this to a uint ptrt. Then we're going to, from pointer, right, subtract that number. And so that way, we obtain the position in the heap that this pointer is pointing to. Remember that the user gives us the pointer to the user section, so it means that we need to go back by however much the size occupies, which is a uint32. And then we're going to have a heap pointer to the block. Perfect. Now, what we're going to do is we're going to say, okay, once I have this block and I want to expand, let me take a look at the next block. So if is free, oh, sorry, wait, let me see. Seems like, ooh, they're about to die. Oh no, they're 9%. Let me put in the other one. Can you hear me now? Yes, I think so. Okay, so we're gonna say, well, if the next block is free, then we're going to merge with it, right? We want to don't assume, assert. Wait, am I assuming some? I mean, yeah. So the reason why I put this here is just like, not like assuming. I mean it more like we are gonna write the code of the expansion. So for now, we're writing the code of expansion, having expansion in mind. Shrinking, we think about later. Because shrinking is a little bit like separate from our expansion branch. So we're just gonna do like if size is greater than size and then like separate them in branches. But for now, I just wanna write the expansion code. Yeah. But it's true. It's better to assert whenever we make an actual assumption. But yeah. So if the next block is, oh wait. Oh no, sorry, never mind. Okay. If the next block is free, then we want to merge with it, right? So we want to call as blocks. Which blocks? Well, the current block with the next block. Okay? The next block of the block. All right. Now, there is a problem with call as blocks, and it's the fact that it asserts that both of them are free, right? In this case, for realloc, and that's exactly what we did here, make sure to not check whether block 1 is free. So block 1 is the one on the left. That's the one we want to expand. So that one could have data. But block 2 must be free so that we don't end up coalescing two blocks that are allocated and thus destroying user data or something like that. Now, we verified that block 1's next block is block 2. So block 1 is the one on the left, block 2 is the one on the right. We calculate the new size, and it says pay attention to this logic when writing realloc. There's no need to set pref free on of the next block 2, since block 2 is already assumed to be free. So this is no longer true, and it's the reason why we included this comment, because we saw far ahead into the future to realize that yes, this is something that changes in realloc. Whoa, RCW PTR, yo, thank you for following. RCW pointer, thank you for following. And yeah, so what we're going to have here is, instead of this comment, we need to set the next block's prev free. So what we're going to do is we're going to say, well, set the prev, so block set prev free of block 2's next block, right? And then we're going to set it to be whatever, you know, and of course it's important, right? Like if block 2 actually has a next block, because it's possible that it's the last block ever, and thus it wouldn't have an next block. Although, okay, this is where we enter a little bit of an issue. Yeah, we need to specialize this. So if it is not a null pointer, that is, this is not the last block, we do that. Else, we set the previous free of of the ghost node, right? And pref free would be set to whatever block 1 is. So bk is free, and then block 1. So we have to be very careful here. Very careful. So the reason is, let me pull up the Scalidraw here. We have these 2 blocks, right? And so what we're doing is, we're going to, for whoever the neighbor of this guy is, so let me copy it and paste it over here. So remember, the next block stores the state of me. The next block is the one that says, is the previous block free? So to know if I'm free, I visit the next block and look at its prev free flag. And what happens here is that here, so if you have, right, if you do this in the last block, there is no next block, right? There is no next block. And so we determine that the information of the last block is going to be stored in the ghost node. So that's what we're doing here. We're saying, well, if this next block doesn't exist, then we set the ghost node to, then we set the pref free of the ghost node. And here, otherwise, if there is indeed a next block, so think of this case, what we want to do is tell the next block, hey, your previous guy is free, or hey, your previous guy is occupied, right? And so what we can do is, yeah, we grab the is free of block 1, because block 1 is now going to become the new header. So now we want to figure out whether or not block 1 is free and include that when we set the pref free. So now the next neighbor knows that its previous, which is going to be 1 after we perform the reallocation, is free or is allocated depending on what the state of 1 is. So what we want to do now is we set the size. This comment is no longer valid. And then everything should be okay after this. Are there any other flags we need to update? The current free, we got rid of it. Yeah, everything is still there. Bobby D1. Thank you for following. Yo, excellent. 81. So, is there anything else we need to do? Let's pay careful attention, because are we getting rid of user data? I'm willing to say no. We are not getting rid of user data. Because we always verify that block 2 is free. We are setting the pref free of the correct things. If we are the last block, then we know what happens. Yeah. Okay. There is a reason why we made the exception that next node would not contain the last block. Why was that? Why was it? Yesterday we were saying that like oh yeah, it was this. It was this. It was this. Um this is great. I'm just going to lurk and listen. Yo, perfect. Yeah, no worries. Just have it in the background. Um so have somebody talking about a memory allocator. And yeah, I don't know, feel free to leave whenever you want and to join back in. Medieval 74 Jester, thank you for following. Yo, guys, we're gaining so many followers. Plus, today we surpassed the 100 followers, which is a very good milestone. So there's a couple of things that are ruined by this. Um, so previously, we have said that next block, right, would return null pointer if you are the last block. The thing is, things are simpler if we interpret the next block of the last block to be the ghost node. Right? Everything simplifies, except for that one piece of code over here that we were looking at. I think it's here. There you go. Where we want the next block, but like the actual next block. If we are the last block, then we don't want to coalesce with anyone. As such, I think that what we're going to do is actually make this piece of code the exception rather than the entirety of everything else. Well, actually, no. I think it's better for the mental model to just keep it like that. No, or maybe not. I don't know. I'm a little confused on what the right decision should be. Um. Yeah. So. And block the order matters. Yeah, no, I think I'm gonna leave it this way. Yeah, just because it helps to be more attentive. So one thing to notice is that we need to make an exception here, right, to know whether or not the block is free. If the next block of my block is a null heap pointer, it means that we are the last block. And so rather than returning that, we return the previous. Well, I guess we can just make a variable, right? We can just say heap pointer t to the end block is going to be equal to if next block of my block is just a null heap pointer, then we want to return arbitrary dot block. Otherwise, we want to return the next block. Perfect. So now we return. Well, I guess there's no need for a variable, right? We can just use this guy here. Control V. And then we K. Perfect. So this hopefully we can enclose in parentheses just to make it clear. And okay, that's all. Oh wait, no. Yeah, there you go. And then we copy this guy and put embark here. There you go. So let's verify that in all the instances we're using next block, we're also accounting for the fact that it could be the last block. So yeah, if this is the last block, yeah, okay. I think a better way to detect whether or not you're the next block would be by just saying next block of my block is a null heap pointer. There you go. So we make good use of it here. That's good. This is the actual function. Here we assert this, which we should be doing. Here we make the difference. If we have a next block, then do that. If not, take it from there. Yes. And then, let's see. Yeah, and then we grab the next block and that should be fine. Okay. So it seems like coalesce does it correctly. If there is a next block, then we set the previous free of that block to be our current state when it comes to freedom. Otherwise, we are gonna grab the ghost node, right? Yeah, okay. A better way to do this that is nonetheless very dangerous because the syntax, the order of the lines matters, despite the lines seeming like they don't, is this. We set the size of block 1 first, and then we set it to be free. Or like, set the is free to be in block 1, whatever block 1's free is. So the reason why this would work, and we could just get rid of this, is once we update the size, then we're going to expand. And once we expand, our next block is going to change. It's no longer going to be block 2, it's going to be block 2's next block, right? So when we call set is free, we're going to set it free to whatever value we already have. And that'll take a dark turn of events. Yeah, no. Let's not do that. Let's not do that. It just makes the code more confusing. Let's not do that. I feel this is way clearer. Right? Yeah, it's like, oh, if you have a next block, tell it we have changed. If not, then go to the ghost node and then set the size. Okay, that seems reasonable to coalesce blocks. And so now. No. We say, well, if the next block is free, then we coalesce with that block. And what else do we do? Nothing else, right? Yeah, we just coalesce with it, and we need to do nothing else. And we simply return the same pointer that the user gave us, right? If the next block is not free, then what do we need to do? We will need to free the current block, coalesce it with whatever's on the left, not lose track of the data in the process, and then yeah, this is really bad. So in our current design, coalescing the blocks doesn't change the information that the second block contains. And that is very relevant. And actually, now that I think about it, we need to do this. If the next block is free and we're able to accommodate for the size that the user is asking for, right? Then what? Yeah, if the size of my current block sorry guys, plus the size of my next block is going to be a little bit of a long condition, and the size of my next block plus the size of the metadata of my next block are able to accommodate for the size, then we do this. But only then. Right? And so now, yeah. Okay. That makes sense, I suppose. I just want to take a look at style for something. Where is remove? We have multi-line ifs. Yeah, I do it this way. Okay, perfect. Then we coalesce the blocks, and then we return the same pointer. Yeah, that sounds fine. Now, if there is no such space, we first need to free the current block and then find another place in which to store the information. So this would be relying on the fact that freeing the block allows the information to persist so that then we can come back to it and actually rewrite it, right? That is not true. And so now I'm actually going to write like a little test. So that's for reallocate on a scenario where there is enough space, but only once the block is freed. There you go. So we have that problem, right? like, suppose there's three blocks next to each other, where, oh, let me erase that, perfect. Where this one's allocated, or sorry, this one's free, and this is the only one that's allocated. And suppose now that the user asks us to reallocate this block, right? And suppose that this block was like, I don't know, maybe like 40 bytes, right? And then they want to change it to 52. Currently, in this sort of scheme of things, we don't have enough space, right? Because this guy is only 40 long. This guy is only 40 long. And so we have no space to accommodate 52. But actually we do. If we free this block and the information's still there, and then we gradually copy the information over here, then we'd be able to coalesce this block with all of these three and thus have like 100 and something of space. So that is the problem. When we have like a moment where space doesn't exist until you free the block you're currently in. So yeah, I guess one thing we can do is like if the current size of your block actually no, okay, anyways, so what we're going to do to solve this is unknown, right? I've absolutely no idea how we can solve this, because to free this block, right, suppose user data is all over here, right? Once we free this block, we need the metadata for the red black tree information to be present. And so now we're going to reinstate that metadata, which means that part of the user information that was written here is going to be gone, completely gone. So that is not good. Yeah, I'm not sure what to do. On top of that, it is unfortunately already 11 a.m., which I have to leave now. I know, really unfortunate, but think about realloc. Think about this problem. I'm going to be thinking about it myself. Please don't use AI to find an answer. Our goal here is to learn. So, get the brain working, try and think of a solution, and yeah, I'll try to think of one too for tomorrow, and we'll see how things go. Okay? So thank you very much, everyone, for joining the stream. Today, we elongated it by 1 hour because we were very excited by the tests we made and how they succeeded. And yeah, okay. So I'm going to say goodbye now because I got to go. But remember, tomorrow, every single day, stream from 7:15 a.m. to 10 a.m., except on the weekends, which is going to be longer. Oh, wait, Juji0908, thank you very much for following, and the same for Hey, it's Austin. But perfect. All right, everyone. It was very nice to have you, very nice to see you, and I'll see you tomorrow. All right. Bye-bye.